Hello all. Welcome to the lecture series on deep learning techniques in medicine. As part of this lecture series, we were seeing about the module 1, the introduction to deep learning. In the previous lecture, we were seeing about how the neurons are connected to biological systems and how they are used in artificial intelligence and what a perceptron is and how the perceptrons are used for deep learning concepts. So today we will see about, in this lecture, we will see about multi-layer perceptrons and support vector machines and how they are used for various other tasks. I am Dr. Sivaranjini, Assistant Professor, Department of Biomedical Engineering, SRM ISD, Katangarathur. Moving on to the lecture, we saw that in the previous lectures we saw and we learned that a perceptron can solve only simple problems. Okay, so if the problems but what if the problems are very complex and the data cannot be separated with a straight line? Okay, so in that case we already saw that an XOR problem cannot be solved with a perceptron. Okay, so deeply visualizing an XOR problem as a graph. So if we plot the values of an XOR gate, so if we are plotting it, the data cannot be separated by a straight line because these two data points belong to one class and these two data points belong to another class, right? These two data points belong to the class 1 and these two data points belong to the class 0. So we cannot separate them using a single hyperplane, right? So when there are cases that there is no single straight line that separates between the two classes, we go for some other networks, right? So what can be the best possible way to find a solution for this? The best possible way is like to stack the neurons, right? What are these neurons? The hidden layers that are present between the input and the output layers are the neurons. Okay, so in a perceptron we have only one single layer in the middle of our input and an output. Now if we are adding or stacking the neurons and making multiple hidden layers, that gives you a multi-layer perceptron. So what is this multi-layer perceptron? Basically, this multi-layer perceptron will be composing of an input layer and a hidden layer and an output layer, right? So this input layer, it is not necessary that we need to have only one input layer, right, in a perceptron. But here it is not necessary we need to have only one. We can have one or more layers of linear threshold units. Here in the perceptrons, we will have only one linear threshold unit. Here we can have multiple linear threshold units and these are called as the hidden layers. So one final layer is the output layer, right? So every layer except the output layer has a bias neuron. So you can see a bias neuron here to a hidden layer and a bias neuron here to the hidden layers, and then the output layer goes on. Okay, so we have it with the fully connected layer next to the next layer too, right? So where this deep neural network comes into an artificial neural network. So when we have two or more hidden layers, then we call it as a deep neural network, right? So when we are having two or more hidden layers, we call it as a deep neural network. And what kind of algorithm that is used to train these multi-layer perceptrons are the backpropagation algorithm. You'll see like what is backpropagation algorithm in the coming slides, right? So on a whole, unlike a single perceptron, an MLP can model non-linear decision boundaries. So it is not necessary that it should be a linear decision boundary. That can be non-linear decision boundary. So that is where your XOR problem can be solved with a multi-layer perceptron, but it cannot be solved with a perceptron. Okay, right? Then we have different types of perceptrons, which are called as single layer perceptron, multi-layer perceptron with one hidden layer, and we have multi-layer perceptrons with multiple hidden layers. Multiple hidden layers in the sense we stack the neurons together for complex applications. So what are the applications that MLPs are used for? They are image recognition, natural language processing, which is the recent trend here now, and we have speech recognition, right? Natural language processing, as you already know, it will be converting your wordings or converting your lexical formats into a understandable format, right? So whatever language which you are speaking in your native language, it is able to understand and give you the context and try to solve many complex issues, right? So how many layers are there? We are having an input layer, a hidden layer that computes intermediate computation and transforms the previous layer weights through a linear sum. So we will see what is this linear summation and things on. So each neuron receives the input from all the neurons in the previous layer and uses nonlinear activation functions. Here in the perceptron, it is only a linear activation function. The main point here is in a multi-layer perceptron, we use a nonlinear activation function, right? So the output layer gives you a final prediction and the activation depends on the task, right? So whether it is a classification task or it is a regression task. So moving on to a feed-forward neural network. What this feed-forward neural network is? So as I told you before, we have an input layer, a hidden layer, and an output layer. And in the hidden layer, the weighted sum of inputs is calculated. So what is this weighted sum? We are having Z1 to be the intermediate portion in a hidden layer, intermediate output in a hidden layer, where the weights are calculated and the weights of each and every input is taken into account and it is summated with every other weights of the second input, right? And we are having a bias term B1. So what happens when you are trying to calculate the activation functions at each and every neuron in the hidden layer? So we are trying to understand how the data flows. First, it moves from the input layer. The input layer gets the inputs. No computation happens. It passes on to the hidden layer and the output comes out with no loops, right? So this is a forward propagation, right? The forward propagation happens from the input, the hidden layer and the output layer. So the process of passing the input values layer by layer and each layer applying a weighted sum activation until the final output is produced, which gives you the forward propagation, right? So how this weighted sum is calculated? We are taking the weights of the input x1, w11 and the inputs, weighted weights of the input x2, w21, and we are multiplying with the each and every weight with its input and added it along with the bias term, right? And then we are giving it as the output to the activation function. So Z1 is passed into the activation function. This activation function can be a linear, non-linear activation function. Similarly, the weighted sum of inputs for Z2 is calculated. So Z2 will be W12, which is the weight for X1, and W22 with respect to weight X2 plus B, and then it is transferred to the activation function. It is passed on through the activation function, and then this activation function, the outputs A1 and A2 are then passed on to the output layer. So here too, the weighted sum of the inputs, which are A1 and A2, is calculated along with the weight. Okay, W1K, the weight W1K with respect to A1 and weight W2K with respect to A2, and then it is moved on to the next portion of the network, which is the activation function that receives the input Z3, and then the activation function is given, and this gives you the output A3, which is the prediction. So the target will be the one which you already know. If, for example, if you are trying to classify a cat and a dog image, so if you are giving a cat and a dog image and you already know it's the image of a cat, okay, so the image of the cat will be the target, Y will be the target, and the output, what it classifies and gives you, becomes the prediction, right? So the target becomes Y and the prediction becomes the output. So how this loss is calculated? Loss is nothing but the error of computation. For example, if the target is a cat, but the prediction is a dog, so there is a loss in the value which it has predicted, right? So thus that loss is called as the error of the entire output, right? So this error value will be the one that is fed back to the hidden layers. Okay, so why this is fed back? In order to train and make the system know what it is learning and to give a proper output, this back propagation goes on. This is what is called back propagation, right? So what is this? Technically, after a forward propagation gives an output, compare it to the actual or the expected output, where you compute a loss, and this back propagation algorithm through which the feed-forward neural networks are trained sends this error back through the network layer by layer, right? So the weights are updated according to the error. Okay, so the weights are updated according to the error, so that the weights are updated in a direction such that the error is reduced, right? So again, I'm saying the weights are updated in the direction that reduces the error, right? We can explicitly say that back propagation updates the weights. This is how the neuron learns from the mistakes, right? So getting into the mathematical formulation, Z is equal to Wx plus B that we saw in the previous lectures. So your prediction output, this will be the output from the hidden layers. So the prediction will be after passing through the activation functions F, where Z is given to the activation function F to get the output, target output, right? So if all the activation functions are linear, then the entire MLP collapses into a single linear model, regardless of the number of layers. How many layers? Even though if you have more number of layers, if the activation functions are linear, then the entire MLP becomes a single linear model or a perceptron model. Okay. So MLPs are trained using backpropagation algorithm, which applies gradient descent to minimize a loss function. We will see what gradient descent are in the upcoming lectures, right? So what are the training steps that I already told you will be the forward pass, right? Forward pass, which will compute the output. So after computing the output, you come back, you find the loss of the computation, you measure the error, and then you do a backward pass or propagate the error gradients, and then you weight update and adjust the parameters according to the error which is obtained, right? So this is what is a MLP. So on a whole, MLP solves non-linear problems by adding the layers, which is different from the perceptrons. But even for problems that are linearly separable, we can find a better line than the perceptron does. Okay, so how come this is possible? This is possible with the support vector machines. They are popularly called as SVMs. So what are these support vector machines? Support vector machines are the ones which are able to classify linearly separable classes or data that are a type of binary classification problem in which two classes, one positive and one negative, can be separated by a decision boundary. Okay, so these are the linearly separable classes. But in a support vector machine, which is also a linear classification model that aims to find a decision boundary with maximum stability. What is this maximum stability? Right? So what this word maximum stability means is like the decision boundary is a boundary that a linear function of the features of the data given that separates the classes. Right? So instead of simply separating the two classes, SVM tries to separate them with a maximum possible margin. Maximum possible margin in the sense, so this is a hyperplane that is separating the two classes. We can have the hyperplanes here or here, right? So which hyperplane will be the best one, or the decision boundary, which decision boundary will be the best one, will be targeted by the support vector machines. So what are we going to do for this? So we are trying to add margin lines that is above or below the hyperplanes. If we are considering this to be the hyperplane, we are adding a line over this hyperplane, or we are adding a line over this hyperplane, such that your margins are closer to the data points that are into the two classes. Okay. So what this hyperplane is, this is a decision boundary line that is separating the two classes, and these support vectors are the data points closest to the hyperplane. Okay, these data points, if we are having a hyperplane here and these are the closest points, these becomes the support vectors. Okay, the ones which are touching the hyperplane, right? Margin lines. These points alone determine the position of the hyperplane, where the hyperplane should be. Okay, so what is a margin? I told you about margin. What is a margin? It is the distance between the hyperplane and the nearest points of a class. We can see with this picture in a better range. So what is this margin? Is like we have a distance between the hyperplane and a support vector, a line that is very near to the support vector. These are the support vectors because these are very near to the hyperplane, right? This becomes the support vector line, right? So this becomes the margin. So whenever you are trying to maximize the margin, your classification or any task that with the support vector machines becomes at a very good performance level. So like the Perceptron, the SVM uses a linear decision function. So the classification decision depends on the sign of this function. So what your decision boundary becomes? As same, Wx plus b is equal to 0. So this decision boundary, we have already seen this decision boundary in the Perceptron, which is a linear model, right? So this decision boundary confirms that SVM is a linear model. The points that are closest to the decision boundaries are called as support vectors, which you already saw. So what happens to this margin? When we are having a larger margin, it has a better generalization and stability. Your stability of the network becomes very good, right? So we have already seen about perceptrons and we have seen about support vector machines. We have seen a brief introduction about what are support vector machines and how they are used, right? So what is the major difference that differentiates between these two, perceptrons and the support vector machines? So perceptrons are the ones which finds a separating hyperplane, but SVM finds a separating hyperplane with maximum margin, right? So unlike a perceptron, SVM does not only aim for correct classification, but also ensures that the separation between the classes is as large as possible. It ensures that your separation is very large, right? So this SVM improves the robustness of the perceptron without changing its linear nature. And one more thing is like what kind of loss function is used in SVM is the hinge loss function, which is similar to logistic regression, which we'll be seeing in the later lectures, right? So SVM incorporates regularization to control the magnitude of the weight vector. Magnitude of the weight vector in the sense how much each and every input is important for this particular task. Okay, so this regularization helps in preventing overfitting, encourages simpler models, and improves the generalization of the model, right? So we have seen like what the support vector machines do and how they differ from the perceptrons, and what is the decision boundary, and what is what our margin is, right? So based upon the margin, your classification task or the task given to the support vector machine varies. So we have two types of margins. One is hard and one is soft margin classification. What is this hard margin? It's like it works only when the data is perfectly linearly separable and are sensitive to outliers, right? So what are these outliers is, so we are having a petal length and the petal width to be classified, okay? So these are the two inputs, petal length and the petal width. So we are trying to spot the two classes, right? So when one class label goes and sits into the next class label, take this as A and take this as B. One support vector, one input alone goes and sits into the next class. So this becomes the outlier. Outlier is like it does not belong to the class A, but it goes and sits along with the class B, right? It goes and sits along with the class B where it does not belong to. So when that is the case, when we are using a hard margin, they are sensitive to outliers, okay? So what the soft margin does is like it limits these margin violations. So here in hard margin, you have sensitivity to the outliers, but soft margins limits the margin violations. You can give the outliers, you can handle these outliers in a perfect way, right? So another important parameter is the regularization parameter C, right? So what is this regularization parameter C does? It does a controlling trade-off between the wide margin and correctly classifying all the data points. Okay, it controls the trade-off between achieving a wide decision margin, that wide decision boundary, because your decision boundary, your margin should be maximized in order to classify all the training data points to a correct level. Okay, so how this value of C should be? So using a lower C value, the margin is much larger, but many instances occur. Okay, so what are these instances? Are the errors, okay? Errors that the system has to tolerate. So for a better generalization and fewer predictions overall, we need a better level of the value C, okay? So better generalization with fewer prediction occurs when we are having a lower value of C. What happens when you are having a higher level of C? The narrower the margin becomes, the stricter classification, and you have the risk of overfitting. All these targets, overfitting, we will be seeing in the next class. Okay, so if your model, if you are trying to use a SVM for your classification task, then when your model is overfitting, you try to reduce the value of C, right? So when you are trying to reduce the value of C, you will be able to get a better result. So having a brief recap of what we saw about the multi-layer perceptron and how it differs from the single-layer perceptrons, and what can be the possible applications of a multi-layer perceptron, and how support vector machines came into picture and what kind of differences that it made in a linear classification problem. Right? Thank you.